Warm greetings to everyone to our fourth lecture in session at the Introduction to Astrobiology online course at Amity University in partnership with Blue Marble Space Institute of Science, Open University UK, and Mars Society of Australia, and also Space for Women. And we have with us Dr. Jennifer Blank, who will be telling us a little bit more about herself and also her topic today, which is where to look for life in the solar system. So let's see, who do we have here? Dr. Jennifer Blank. Jen Blank is an astrobiologist with NASA at the Ames Research Center in Silicon Valley. She is also a senior scientist with the Blue Marble Space Institute of Science and an adjunct professor at the Center of Excellence in Astrobiology at Amity University, Mumbai. Jen's research has focused on water and rock chemistry derived from volcanic rocks that support microbial life and the mineral biosignatures this life deposits. Currently, Jen leads the NASA Braille project, a study of life and a robotic mission to detect life in volcanic caves. Her team is preparing for a future mission to a lava tube on Mars. Jen has worked as a member of the Mars Curiosity rover science team, planning science operations for the ChemCam laser instrument on Mars. She holds undergraduate degrees in geology and English from Stanford University, an MS in oceanography from the University of Washington, and a PhD in geochemistry from California Institute of Technology. This year, she was selected as Global Mentor for the United Nations Space for Women initiative. So Jen, firstly, congratulations on that. I didn't know that you were selected this year, so I think that's a great thing to know. And over to you.
Thanks, and welcome. And please bear with me as I talk to myself. But I look forward to seeing questions in the Q&A. Okay, so the topic of this week's lecture is where to look for life in the solar system. And I hope if all of you were asked that question, you would answer with the most obvious answer. And that is on Earth, because we know we can find it here. And but really the topic this week is to look for life beyond Earth in our solar system. I'm focusing just on our solar system because there are many potential candidate sites. And also we're learning more and more about our solar system from ground-based telescopes, from space telescopes, from orbiter missions, from flybys, and from landed missions on Mars and on the Moon. So this search for life beyond Earth is based on life as we know it. And that's just sort of following up from Michael's, or Dr. McKay's lecture last week, when he talked about Earth and Earth's early life and the rise of life on Earth. All of our sort of intuition and knowledge that guides our search for life elsewhere really is derived from what we know about ourselves and about our planet. And so because of that, we believe that the requirements for life are the following. We need liquid water. We need biogenic elements, carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, and minor amounts of different metals. We need energy to feed and support this life. And we need a way for these ingredients to congregate and reproduce and transform or evolve. So I'm not going to be talking about silicon-based life forms. Actually, I'm not going to be talking about life forms really because we have not discovered life beyond Earth at this point. So if we look at our solar system, I really like this diagram because it shows a few things. It shows the relative proportions of the 8 planets in our solar system, sorry to Pluto. And it also shows some dimensional information. It has the radius, just my pointer here, radius, the mass relative to Earth, the time it takes to go around our sun in Earth time. And then, so that's pretty common, but pretty normal. But at the bottom, it also shows essentially the eccentricity of these orbits. So if it be on this line going from our sun out in astronomical units out to about 15, where 1 astronomical unit or 1 AU is the distance from the sun to the Earth. And so everything's measured in Earth-Sun distance. But it's based on how thick these bars are, it sort of gives you an indication of the eccentricity of the orbit. So Earth is pretty symmetrical, circular orbit. Mars has a slightly eccentric orbit. So if you look at Mars here, So we'll go down here. It's a little bit more pronounced than a dot. And as you go further and further away from our sun, the orbits of the planets and of the dwarf planets become more and more eccentric. In other words, more elliptical. So look at this one, for example. This is Ceres, which is a dwarf planet in the Kuiper Belt. It goes from about 6 to almost 15 AUs. So it's a really wonky orbit. And this is sort of interesting in terms of thinking about how we might plan to visit some of these places and how long it might take to get to visit some of these places based on when we departed from Earth. You can see, let's see, Earth orbit is 1 year. Mars orbit's almost 2 years, twice as long to go around the sun. But then when we get out here to Neptune, it's 165 years to go around the sun. It's a long time. So where to look for life? In the early days, and by early days I mean, as recently as about, gosh, I think about 30 or 40 years ago, we thought we would have to find life in a zone where there was liquid water on the surface of a planet or a body. And that holds for in our solar system, and also if we could find planets beyond our solar system or exoplanets. And so this was known as the Goldilocks Zone. In other words, not where it was too hot, not where it was too cold, but where it was just right. And the example for this was given in these are 3 rocky planets, Mercury, Venus, Earth, and Mars, where we have Venus too hot, so we don't see liquid water at the surface of Venus. Mars too cold, where we rarely see liquids at the surface, mostly ice. And Earth, where we have 3/4 of the planet covered with water. So it's just right. And this comes from the children's story about Goldilocks and the 3 bears. I think most of us grew up with this story. So what we've been discovering more and more is that a lot of these bodies in our solar system, whether they're asteroids, dwarf planets, moons, they may be rocky at the surface, but they actually seem to have some kind of liquid water interior. So this sort of essentially shreds our idea that we have to have liquid water at the surface to be habitable, because they could have, from life under the oceans and hydrothermal vents and things, that we find life under the surface thriving. So in this picture, you see our current situation where we have our sun and we have this habitable zone sort of is defined based on that liquid water on the surface. You can see it's a pretty narrow margin. So when when the first exoplanets were discovered, we thought, oh, they're not in what we calculate to be a habitable zone, so they wouldn't have any potential for life. But this zone, or this disk, I guess it's like a frisbee ring, it's changing. And also what's also changing is our sun is getting warmer as it gets older. So as in about 8 billion years, our sun will be a lot hotter, and that means that the habitable zone will be pushing further away. It'll be warming more further out in our solar system. So that means that Earth and Mars will both be too hot, and Jupiter and Saturn will be just right. Now, since these planets are known as the icy giants, it'll be interesting to see what happens to their chemistries, but also it might mean that the moons associated with those planets in 8 billion years might have liquid water on their surfaces. That's kind of interesting to think about. So this diagram from the Planetary Society is really one that helped me to think about where I would pick to look for life in our solar system. And you can see it's cross sections of the different bodies in our solar system. And what I think is important to look at is how many of them have these light blue rings that indicate the presence of liquid water beneath the surface, liquid water or ice beneath the surface. So that's pretty exciting. Now, how do we know the planets and moons beyond Earth have liquid water when we haven't landed there and we haven't sampled there? Well, we can observe from ground-based telescopes on Earth, parameters like the details of the orbit, the periodicity of the rotation about the axis of the body, any kind of bulge or asymmetry in the body, and moments of inertia. These all allow us to calculate cross-sectional compositions of these different bodies. And so all of these pictures are based on model compositions, with the exception of Earth, where we have seismic information too. And now on Mars, with Mars InSight Lander, we have a 1-point seismic station. And also there have been there's been a small seismic array deployed on the moon. So all of these are models, but they're pretty exciting to me. And here I've put a check by 8 of them. And so other than Earth and Venus and Mars, where we might have once had life or have life, or might have life in the future, these are all bodies that I would choose if I had to pick where to go, because oops, I shouldn't have checked IO, because they have liquid water. So that's going to guide my selection for where to go look for life, where I'd recommend we go look for life in our solar system. So, throughout this talk, I'm going to keep coming back to these pictures that I've pulled from the internet of different renditions of our solar system, just because you might, like me, might not always think about the order of the planets or how many moons they have or what their relative sizes are. So anyway, here's another picture. I like this one. It shows the sun in the middle, tiny sun, and then it shows the rocky worlds of Mercury, Venus, Earth, and Mars, and then going out to the icy worlds after the asteroid belt, and then hitting this next thing called the Kuiper belt, right, which is where Pluto is these days, near the Kuiper belt. So here's our inventory in a nutshell. And this is changing all the time because we keep finding more moons and more things at the far reaches of our solar system. But as of this summer, you can check at this website I've listed at the bottom, we have, Earth has 1 moon, Mars has 2. The asteroid belt has a new dwarf planet, or rather it's one of the bigger asteroids. It's called Ceres, and it's been recategorized as a dwarf planet, has no moons. Jupiter has 79. And in the brackets, I've listed the Galilean satellites, the biggest ones. Saturn now has passed Jupiter with 82 moons. I think students found 20 moons in 2019, so that helped bump Saturn up in the moon department. And the biggest ones there are Triton, Dione, Enceladus, and Ames. Uranus has 27, Uranus. Neptune has 14. And I put there Triton as the biggest one. And then we have the dwarf planet Pluto, and it has actually 5 moons if you count Charon, which seems to almost be very, very close in size to Pluto. And the dwarf planet Haumea has 2 moons, and these other dwarf planets listed here all have 1 moon each. And we may find more as we continue to explore, but for now, our solar system has 8 planets, 9 dwarfs, and 218 moons. Here's a picture of them, so you can see that a little bit, just showing their relative size. Think about size relative to our Earth, which is about 1/10 the size of the moon. So here's Mercury. So some of the moons are bigger than Mercury, so bigger than a planet. Ganymede, Callisto, Io, and Europa are the Galilean moons of Jupiter, so the biggest ones. Titan is the biggest moon of Saturn, and Triton is the biggest moon of Neptune. Sorry, did I say maybe it's Uranus? Okay, so now to summarize, where to look for life in our solar system. These are the top 10 candidates. Now, some of you, if any of you attended the workshop in February that we gave in Mumbai, you might have seen a similar talk to this, where I didn't include Venus on this list. I felt compelled to include Venus because of the recent news about the detection of a biological compound that makes people very excited to go look for the source of that compound in Venus. And I'll talk about that in just a minute. So Venus, Mars, Ceres, Europa, Ganymede, Callisto, Enceladus, Titan, Triton, and Pluto. And I'm going to just essentially give you a sort of a pictorial visit to some of these, or to all of these, and just tell you a few features. I really recommend going to NASA and ESA in particular websites where they have amazing photo galleries and collections and lots of fun facts about these bodies. So Venus. How many of you read about discovery of compound of interest in Venus, a phosphorus and hydrogen compound? It was just in the news this month. Now Venus is almost the same size as Earth, but it doesn't have water in the atmosphere. We think that most of the water left Venus, or all of the water left Venus, via photoionization at the upper atmosphere, and then loss of the hydrogen due to Jeans escape, which means that the mass of hydrogen is so little it can escape the gravitational pull of Venus. So now the atmosphere of Venus is mostly CO2, and the pressure at the surface is actually 60 atmospheres of pressure of CO2. So it's quite a different environment. So this new molecule, or the molecule was recently detected or recently reported, is phosphine. And here's a picture of the phosphine. So it was connected, or rather determined, based on one spectral line. So from a terrestrial-based telescope, corresponding to a single rotational transition. Now this was confirmed by multiple observers, multiple scientists. So it's there, and we wouldn't expect to see this molecule produced abiotically. So that means, was it produced through a biological pathway, or is there an abiotic pathway we don't know about? So it's very exciting, and yet I don't think it tells us there's life, but I think it actually will help persuade some of the space agencies to prioritize missions to Venus. And this might be the case for India. What do you think, Sid? All right, I'm gonna move on to Mars. Here's a picture of Mars. And now Mars, this is a great image from the Planetary Society again. They made these exploration family portraits for different planets in our solar system. And here you have all of the orbiters that have gone to Mars around the planet here. And then on the surface you have the landers that have actually landed and functioned for a respectable period of time on the surface of Mars, rovers and landers actually. And you can see the flags of the different countries. So a lot of countries have made it to Mars, but very few have made it to the surface. Now, there's a reason that Mars, and Mars is my #1 choice for where we should focus our energy, look for life too. But if you look at the surface of Mars, there's a lot of evidence that's reminiscent of water produced or fluvian features, or we see on Earth, right? So a lot of evidence of imagery and morphology that suggests that water was once present on the surface of Mars and is no longer there. We see these channels, we see riverbeds, we see braided streams, we see lakes, we see different, I guess, old shorelines, and these are all reasons to go look for water on Mars. In fact, a lot of the more recent missions of NASA, at least, were not looking for life on Mars, but looking for signs of habitability. So here's another Planetary Society image showing the Mars landing sites and Mars past and future landers and rovers that will be on the red planet. So you can see in the orange, you have the landers that have landed or are still acting on land. The Curiosity rover is still going here, and the InSight lander is still active on Mars. And then in blue, you see the Perseverance rover, the Tianwen-1 rover, and then the Rosalind Franklin and Kazachok rover that we hope will launch next year. So a lot of activity, but still only covering a very small fraction of the planet. But most of these missions are focused on characterizing the structure of the planet, the chemistry of the rocks, and really not since the Viking landers was there an ability of any sort of lander or rover to look for life or detect life. Curiosity focused on habitability and actually was very successful. So here are some images from the Curiosity rover that landed in 2012 and has been working on Mars for, over 8 years now, and still going. And you can see in this picture on the left, it landed in a big crater and was going to look for, essentially, track along a stratigraphic horizon and essentially wander over almost 1 billion years of Martian history as evidenced by the depositional record on Mars. So here you see the arm of Curiosity in black and white here, pointing toward the first drill site that the rover did on Mars. And the cool thing is that right within the first few months, Curiosity drilled successfully, and it had an ability to bring that drilled material on board to the rover and then X-ray it, and from that, not just tell the chemistry, but tell actually the crystal structure of that material. And so and one of the most exciting finds, or if not the most exciting find of this mission, is they found that the rocks were clays, and these clays would have been formed in water that was drinkable. So yes, we've shown that Mars was habitable at one point. Mars would have had water that we could have been drinking at one point. And so over the course of its the first billion years, the water has gone away. Now we see the surface as it is today. So the site, excuse me, the site in Gale crater was interpreted to be an ancient lake or shallow sea, and we didn't have the capability to find microbes here, but it was very exciting that this was a more alkaline environment that would be hospitable to life as we know it. And here's a selfie at the lower right of Curiosity. So the next missions, Mars 2020 that launched this July, and ExoMars, Rosalind Franklin will actually carry instruments that will be able to detect organic compounds and potentially life. So that's pretty exciting. Curiosity, meanwhile, has continued to rove. It's drilled 27 holes and traveled about 23 kilometers over its long mission, and it keeps drilling every so often. And you can see from the color of these are the drill cores, right? So the colors of these are the different drill sites. And based on if it's a red color, it's more oxidized, which is less amenable to life as we know it. And then when it's sort of the blue and the gray, that's more alkaline, rich material that's more hospitable. And so we see a vast color variation here. And all that's an indication of different minerals, different chemistry, and the different ability of these different stratigraphic units to not only record the different geologic periods of Mars, but the types of rocks and types of environments that were present in Martian history. So here's a picture of the Mars 2020 landing site, Jezero crater, and also a little postcard of the Perseverance, Percy rover. And I'd recommend if you go to the site, the Mars 2020 website, you actually can see the cartoon of the capsule traveling through space, and tells you down to the minute when it's supposed to land. So I check from time to time. It's kind of fun. Anyway, one thing we do on Earth, since we aren't able to go to Mars in person or go to these other sites, we do what we call analog studies. And I put this picture in the lower right. This is Lonar crater in India, because some of us, with Sid's leadership, have been starting to study Lonar crater as an analog for the Jezero crater site. Now the aspect ratio is very different. Here is the delta here in Jezero crater, and the rover is going to land about here. Here is a much smaller 1 kilometer size crater in Lonar crater rather, and it does have a delta, and the host rock is very similar. Lonar crater is hosted in basalt, as is Jezero crater on Mars. So when we look at analog sites on Earth, we know that they're never going to be the perfect mirror of that site somewhere else, but it gives us an ability to look at some of the parameters and maybe gain better insight into processes that could be happening on other planets and bodies. Okay, now I'm going to take a small break as I mentioned analog work, and tell you about something that's been taking up most of my research time lately, and that is work on a Mars analog site, which is a volcanic cave. And I lead a project called Gale, and we're starting our 4th year, and we work in a site in Northern California where there are over 800 lava tubes. So Gale stands for Biologic and Resource Analog Investigations in Low Light Environments. That phrase was coined by a fellow NASA colleague who loves acronyms, so I got help with that. Anyway, it was a combination of things where we went as scientists into the caves and spent many weeks underground collecting samples to do all sorts of comparison studies of the life there, the chemical signatures the life leaves behind, the mineral signatures the life leaves behind, these are known as biosignatures. So even after the microbes die, they might leave some indication they were once there, and also characterize the rocks and the chemistry and the mineralogy of the features in these caves. And then use that to help guide a mission, a sort of artificial mission. So here's just some pictures of things that we saw in these caves. So we have little biological microfilms, we have little, we call them cave corals, except these features are almost all silica. So they look like they might be a carbonate mineral like you'd see in the ocean, but they're mostly silica. But that's cool because that means they have a higher chance of persisting over geologic time, because silica minerals or silicates are more resistant to weathering than carbonates. Anyway, we see these microbial crusts, films. We see these are other little polyps that are hot, rather hard. We have to scrape off with a knife. Here's for scale. Here's one of my colleagues, Dr. Dada, at UT San Antonio, standing there with inside ribs of one of the caves. And so we studied this for a long time and took pictures and are correlating something we're calling a mineral microcontinuum, which is to try to understand as we go from what looks to be bare rock, but we know now is covered with a very thin microbial biofilm, through different rock features that we define as coralloids, crusts, polyps, little fingers, cauliflowers. We have very sophisticated names, microbial mats, and then oozes. As we go to mostly rock to mostly soft material, can we define something that where we can predict how, what concentration of DNA we would find, what microbial species we would find, what mineral chemistry we would find, what isotope chemistry we would find, and then essentially present this as a matrix to NASA and other agencies to help guide their search for biosignatures on planets where there isn't any active life today. So that means if we start out with an ooze or a film or mat, and then those go away, these mineral signatures or biosignatures will still be left behind. So we've in conjunction with that study of people in the cave, we also have a mini mission where we're actually two of these now, where we sent a rover into one of the caves, and that rover collected data that it sent back to a surface team, and that surface team had not been in the cave. So the surface team had to look at a small section of the cave wall with blinders, and then, predict where, or rather direct the rover where to go back and do additional diagnostic tests on the side of the cave wall. So that's an ongoing study that we're working on with Gale. But in the meanwhile, we go back afterwards to see where the surface scientists picked as the targets, and then we did the same exercises with people in the caves, and that's how we try to make a statistical comparison. And then what we're doing now is we're using all of the laboratory data and all of the more than 10,000 pictures we've collected we've developed a training set for the creation of algorithms that now we're going to deploy on an autonomous rover. And so we just did a scout mission this summer where we sent, actually just earlier this month, due to lots of delays, we sent the Spot rover into one of the caves, and Spot is walking in this scout trip. Actually, we're just trying to see if Spot could walk in, and Spot didn't fall over, which was great. And now next time we'll go in and we'll try to deploy this algorithm to see if Spot will pick out targets on the wall that would be similar to the ones that the scientists would pick out as places to go look for life. So we're pretty excited about that. Oh, and I have to just say that that's the last analog slide. But I have to say that NASA doesn't have any mission to Mars on its to-do list, right? But the way you get a mission started is you have to jump through many hoops, and it takes many years often to get a mission to another planet if you're lucky. And so we're trying to show that it can be done, and that just essentially set some of the groundwork to encourage and support a future mission to a Martian cave. So in recent meetings and workshops, however, the broader Mars community has recommended targets in the search for life on Mars. We haven't found life on the surface yet, and it seems as though the life on the surface of Mars, rather the conditions on the surface of Mars, would be hostile to life as we know it. Mars doesn't have protection from radiation. There's no liquid water. It's very cooled. It also has perchlorates and other compounds that might oxidize any organic materials, including life forms. However, there were 4 sites that were proposed by the community as places to target, and they're ice, so deeper in the ice, in salt, in these salt deposits that might shield you from radiation, in the deep subsurface that you could access by drilling, but having to drill a few kilometers, and volcanic caves. So we're very pleased, and also supporting, advocating for this option. But we're pleased that the community recognized volcanic caves as one important target to consider. So that's good. Okay, I'm going to keep going now and move on into the asteroid belt. So here we see we just finished Mars, and out beyond Mars is the asteroid belt. Now, some of you may have read about the dwarf planet Ceres that was upgraded from an asteroid to a dwarf planet in 2006, and it's the only known dwarf planet in the asteroid belt. It has a low density consistent with the composition about a quarter of this body being water. So that's sort of interesting. And the other thing what's interesting is that Earth-based observers noticed this little sparkling or very bright high albedo glint on the surface of Ceres in this little crater, and didn't know what it was. So the NASA's Dawn mission studied Ceres from 2015 to 2018, made multiple passes by, and they found that material is actually sodium. It's a sodium carbonate in the material. Here it is. Here's that shiny bit again, and here's a false color rendition of that image. And by doing modeling, they concluded, or investigators concluded, there must be some kind of briny liquid material underneath. So here we find maybe potential for some sort of liquid environment that's not too far away from Earth in terms of solar system distance, and might be a place where you would find a liquid ocean or liquid puddles or liquid pockets under the surface. So that was pretty exciting. Okay, moving out to Jupiter's Galilean satellites. And these are satellites we can see actually with amateur telescopes. And in fact, in 2009, we could buy, I did for $11, we could buy an imitation or plastic rendition of the telescope that Galileo Galilei used to identify these moons in 1610. So that's pretty exciting. But we know there are many more moons orbiting Jupiter today. NASA had the Galileo mission to Jupiter that lasted from 1989 to 2003, and it made between 8 and 12 passes of each of these larger moons. So Io is very close to Jupiter, so they're shown here in increasing distance away from Jupiter. And Io has a lot of sulfur on the surface and doesn't have any water that we can tell, and has very high radiation. So I'm not going to do not pick Io, but I'm going to look at the next 3 of these moons. And some of you may recognize Europa as being one that's targeted for a future mission already. So here's Europa. It's about 90% the size of our moon. The model suggests that it has an iron core and then a rocky mantle and salty oceans, and a subsurface ocean that's 10 to 15 kilometers beneath that surface ice. And one of the 2 exciting things about this is that there's a suggestion that heat from the tidal forces of Jupiter could keep a subsurface ocean liquid. And they've also observed water plumes erupting up to 160 kilometers from the surface. So this moon may have more, actually it's been predicted to have 4 to 5 times more water than Earth in total. And there may be, because the surface doesn't seem to have very many impact craters, this may mean that there's recycling on a pretty frequent basis of material between a deeper salty ocean and a surface. So here's our artist's rendition, and I'm going to show you a sort of montage of surface features. But and here you see the sort of these, are they blocks of ice? Are they ice tectonics? But what to note in almost all of them, with a few exceptions, are that we don't see a big cratered surface. This one corresponds to this impact crater down here. So here's the artist's model of the interior of Europa. Again, having some kind of metallic core like Earth, and a rocky interior, and then a water layer. So people have proposed all sorts of things like hydrothermal systems, black smokers, bringing life up to, rather supporting life in the oceans, the subsurface oceans of Europa. And because this hypothesis of subsurface ocean on Europa was first proposed based on the Voyager flybys, so some decades ago, Europa has been essentially a subject to a lot of dreaming, a lot of excitement, in a place where we could find liquid water far, far out from the Goldilocks Zone. Here's just one more picture showing another artist's rendition of these black smokers. All right, moving out, Ganymede. Now, when I was a girl, I read a lot of science fiction, and Ganymede was often attributed to a place, as a place that would be a good place to colonize. And I'm not quite sure why Europa is a higher candidate, except that the surface is cleaner, and you can see that it is ice, whereas Ganymede has a rocky mantle and sort of seems to be half rock and half ice on the cover. It's not sure, we're not quite sure what's happening there, except that it's very dark compared to Europa, dark in color. So either has a lot of dust or something else, we're not sure. But here's a picture of Ganymede compared to Jupiter rather, and you can see this is the only moon in our solar system that has a very strong magnetic field. In fact, we've been able to see aurora from Earth coming or emanating from Ganymede. But likewise, tidal heating from Jupiter could help maintain a liquid subsurface ocean. Here's some more pictures of Ganymede. This is a false color image on the left, and here it shows that Ganymede has these two types of surfaces. One is this old cratered surface, and I don't have a scale here, but you can kind of get an idea based on this picture of the moon here. Ganymede's it's bigger than our moon actually. And then here below is a groove surface with fewer craters that looks a little bit more like Europa, but still you can see lots of small craters. So maybe that Europa is a more attractive candidate because Ganymede doesn't seem to have as much activity refreshing the surface. And here's an artist's rendition of a model of the interior of Ganymede, which is about half rock and half water. So very thick amount of water. And finally, of the 3 Jovian satellites, we have Callisto. So it's the second largest after Ganymede, orbiting Jupiter. There doesn't seem to be very much activity here, though, because the whole surface is polka dotted with craters. The Galileo spacecraft did detect an ocean located much deeper than these other 2 satellites, at about 250 kilometers depth. So it does have a slightly thicker action of atmosphere, rather, of carbon dioxide, hydrogen, oxygen than the other 2. So I still think it's a candidate. Just that 250 kilometers depth is would be hard to get to. All right, we're going to move out after that and go visit the Saturnian moons, or 2 of them actually. Here they are. Here are the larger ones in profile. You can see that Triton really dominates the moon family here, with the kilometer about 10 times that of Enceladus, which is only about 500 kilometers in diameter. So Enceladus is here. Now Enceladus is the one with the tiger stripes. It's pretty exciting. And what was even more exciting is that the Cassini's instruments were able to first see plumes emanating from the surface of Enceladus, and then actually analyze the chemistry of the plumes. So that was pretty exciting. They found water vapor, methane, CO, carbon monoxide, carbon dioxide, and simple and complex organics, so aliphatic hydrocarbons that are coming in this plume. And a lot of people are very excited about Enceladus as a place to look for life because we actually see the organic compounds there. I just want to point out one thing, is that Enceladus is probably four years further out than Europa. So I can see why you'd be excited by this, but Europa also has smaller plumes and also a water ocean that's closer to the surface. And so I'd probably pick Europa over Enceladus. And that's just my 2 cents. The other one is Saturn's Titan, and Titan's just the real outlier of all the moons in our solar system because it has an atmosphere. It's mostly nitrogen, but also has what we think are hydrocarbon-rich clouds that may be raining debris or dust down to the surface. So it's really different than anything we know about on Earth or anything we've seen anywhere else in our solar system. The ESA's Huygens probe landed on Titan in 2005 and collected data as it made its way through the thick atmosphere. So here's a picture of the icy cobbles, or it looks like rounded pebbles, near the landing site of the Huygens probe. And then other pictures from Cassini show liquid ethane lakes. So essentially some sort of fluid system, but it almost like antifreeze, so nothing that we're familiar with. But people have proposed that there could be a new life form there. And like many of these other worlds, there seems to be a liquid ocean in the subsurface. So here's a cross-section of Titan. And gosh, Cassini flew by many times. But this is so exciting to think about. There's really unusual chemistry on the surface, and then, excuse me, and then a subsurface ocean too that could support life. So this is spurred on the Dragonfly mission that was selected recently to continue development and is planned to launch in 2026. And that's going to be there's going to be a helicopter that's going to bounce around on the surface of Titan and look at the strange moon. So that's pretty exciting. Okay, so let's see. We've gone to Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, and now what's next? Uranus. Okay. Oops, is that right? We're going to skip Uranus and go to Neptune. Neptune's Triton. Okay, so here's a picture from the Voyager flyby. And just recently, actually, I know the person who's the chief scientist for a new mission, the Triton mission, was just selected to fly by Triton in 2038. What we see here is we have this weird surface, sort of dual surface textures again. We have nitrogen ice and partial resurfacing of the planet. So this seems, based on the resurfacing and the lack of craters on part of the planet, seems to be the youngest surface of any of the icy bodies in our solar system. It has a very intense ionosphere, and we know on Earth and elsewhere that when you have ionized gas, you have a lot of chemistry, a lot of chemical reactions. So that could be interesting and certainly different than other moons we know about. But the whether or not this moon has a subsurface ocean is unknown. Here's just a close-up of what they're calling a cantaloupe or a melon texture. And also here's a fun fact. The initial observation of Triton was supported by a brewery money, so someone who was a beer maker in 1846 by British astronomer William Lassell. So I thought that was kind of fun. Anyway, okay, there we are. We've gone to the major rocky planets and the icy planets and the asteroid belt, and now what happens is we continue to go out further from the sun, our solar system. Well, of course, I have to mention Pluto. Even though it was degraded or downgraded from planet status, we did have the New Horizons flyby about 10 years ago in 2009. That was pretty exciting because it went from being just a black body we didn't know anything about to a planet with ice and an atmosphere and mountain ranges. It was very exciting. So here, but now it's classified as a Kuiper Belt object, or KBO. So here's a picture from the New Horizons flyby. You can see this rugged crater terrain. You can see these are like nitrogen ice flows and polygonal ice cells. So that means there's movement on the surface and signs of textures and morphologies of pitting around the edges, suggesting convection cells. So there's some kind of activity, which is exciting. And here's an artist's rendition of Pluto's surface. So we see on Pluto evidence of ice and smooth portions. We know it has a binary orbit with its largest moon, Charon. And Charon actually has a methane atmosphere, which is interesting. Pluto seems to have evidence of a subsurface ocean, and its own, as I mentioned, a very thin atmosphere of nitrogen, methane, and carbon dioxide. So, there seems to be water water and other types of ice everywhere. And in the subsurface, there seem to be many candidates with possibility of liquid oceans, and therefore the possibility of life as we know it. So here's a picture of Charon. So it's about half of Pluto's diameter, and so it's really unusual in the sense that it's so big relative to its associate dwarf planet. So it's still called a moon. It's one of 5 moons of Pluto, but it's almost like a twin, a dancing partner. Okay, let's go back to this picture, and please excuse me, this is a mistake here. And let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I missed one. Anyway, here at Callisto. There we go, Callisto. Anyway, here are the 10 places to look for life in our solar system, according to me. And if any of you disagree with me, I'd love to hear about why, and or suggestions on where else you would look. So I'm going back to our solar system, and I'm going to show this diagram again because I think it's so great with these eccentric orbits. So when I think about where to go look for life in our universe, or sorry, in our solar system, again, I think the priority should continue to be Mars. And I think we have a lot of places to look on Mars, and also Mars is close. Mars is 6 months away to 8 months away. So, but now that we know about Ceres and the asteroid belt, that might be another candidate site that wouldn't take too much longer to visit. So I will end here and just say thank you for listening. And I hope you enjoyed our little sort of tour through the solar system, brief though it was. And I hope this will inspire you to go online and look at different photo galleries, because you can really get lost and dream about where to look for life on other moons and other worlds. And also, it's better than watching TV. All right, thanks a lot.
Thanks a lot, Jen. That was amazing. In fact, some of the images I was in fact seeing for the first time. So I need to borrow those from you for my future talks as well. So that was great. And also,
actually,
the last
may I just say thank you, Sid, but may I just say also that there's so many, it's so cool to read about the older missions. Yeah. And Sid is going to talk to us about space missions and planetary missions next week, and so I'm really looking forward to that.
Yes, absolutely. Next week we'll be talking more about the missions and what are the different kinds of challenges faced by these missions, whether they're flying by these worlds, or are they landing on the surface, or are they just in orbit around them, observing remotely. So that's all going to be next week. So let's take a minute now to relax, and slowly I'm going to start browsing through some of the questions. That was good timing, Jen. So we do have, in fact, time for a few questions if you're up for them. Let's see, what do we have? Okay. And for those of you whose questions get skipped or are missed, it's probably because we just want to focus on some of the very diverse questions that have been posted that are allowing the audience to kind of get a better understanding of the topic. We will try to answer all of the questions that have been posted. Many of the questions, normally, you can find information just by going through the internet, but we will still respect the fact that you have asked us that question and point you in the right direction. Okay, so let's see. Chirag asks, what makes us to believe that if the planet, what makes us to believe that the planet is to be? Okay, so I think the question is, what are the most immediate criteria that needs to be filled for a planet to be looked at for life? I think you've answered a bit of it already, but maybe.
Right. In fact, Chirag's question was before I even started, so yes. I actually mentioned it. Yeah.
And you also posed the question with relation to boron being on its surface.
So which planet has boron on the surface? I know we found boron on Mars. We found boron in Gale crater with the ChemCam instrument. Is it possible that it will be having life soon? Well, I think many things are possible. We've had suggestions on Earth life that some elements can substitute for others. There was a suggestion that arsenic, for example, could substitute for phosphorus in some of the DNA structures. Doesn't seem to be a primary substitution, but so they're definitely, I would certainly be open to other types of life forms, other types of structures.
Mm-hmm. Great, thank you. Next question is from Zoe. Is it important to bear in mind potential life forms that don't follow these rules, or because it doesn't follow our definition of life, would it be classified differently?
Zoe, that's a great question, and I think I tried to mention at the beginning how our search for life is guided by life as we know it. Now, that has some limitations, right? Because we might miss something, but we don't know what it is we might be missing. So as we structure and plan any sort of mission, we really need to have it based on facts, or rather planned, looking for observations that we would expect or think about. So we limit it to life as we know it, and wouldn't it be wonderful if we're surprised?
Great, thank you. Here's a question about Venus. You'd be almost certain you'll be getting some Venus questions your way. So Abigail asks, is Venus too hot because of its runaway greenhouse effect, or because of its position, I think the proximity to the sun, or is it a bit of both?
I think you're absolutely right that it's a bit of both, right? I mentioned the fact that we think that Venus did have much more water in its atmosphere, but because, and this is happening on Earth, and actually the MAVEN mission, NASA's MAVEN Mars orbiter is, and I think actually the MOM orbiter from Israel is also studying the loss of the change of the Martian atmosphere. But what happens is, as the atmospheric gases rise up to the outer part of the atmosphere, they're bombarded by solar radiation. It breaks up and ionizes those gases, and the very lightest elements or molecules escape. In the case for water, it would be hydrogens escaping as water is breaking down to oxygen and hydrogen. So that means because it's closer and hotter, Venus lost water a lot faster than Mars, and even Earth is losing water right now. Mm-hmm. And then there's more carbon, and then you do get the greenhouse effect. So a bit of both.
Great. And I see that you have access to the questions as well, Jen. So feel free to choose one that you think would be exciting, because all of them are really good. Some of them are yes or no answers.
In terms of astronomical distances, the moon is also in the Goldilocks zone. So why is there no life on the moon? That wouldn't it be cool if there was? Well, we think we just don't think there isn't liquid water on the moon, and this has I think in large part due to the moon, the way the moon formed, right? So we think now that the moon formed from a collision of Earth in its early history, and then one piece was bigger, and that was Earth, and then the moon, essentially the dust that coagulated and essentially accreted to form the moon, and there just isn't very much water on the moon. We have water that came from comets in the form of impacted ice, but it didn't have that kind of sort of regime and surface water, deep water, tectonics, whatever, to have energy that could support life. But we know, who knows, we might find life in the ice. Wouldn't that be cool? Oh, someone says, ma'am, if I'm not mistaken, you demonstrated an experiment on the documentary Nova Origin of Life. Srividya, thank you so much for watching that. Yes, it was. I've had many interesting wiggles in my path as a scientist. And for some years, I actually I did impact experiments where I tried to simulate a comet hitting the Earth in the laboratory. And actually showed that we could make peptides from amino acids in that energy from the impact. And that was a featured episode of Nova. And actually, I didn't mention comets. What about comets? And I didn't mention the Oort cloud, which is this kind of imagined sort of repository or of ice, mostly icy bodies, very, very far out at the very farthest reaches of our solar system, where comets live. And every once in a while, another sun will get close enough to knock a comet out of its orbit, and then it will come into our closer to the sun, and start on a path, and eccentric orbit about the sun. But again, thinking about source for water, source over its lifetime, where the water would become liquid as it approached the sun. And I don't know. I mean, I think it'd be hard. I think it'd be hard to maintain life unless something went into deep hibernation for 100 years and then defrosted and came out. I think that's possible, but anyway, it didn't make my top 10. Okay. Let's see. Other solar systems in our galaxy have seen gas giants orbiting close to their suns. I wonder how these planets are maintained given their proximity to their star. Yeah, you mean, are you meaning would they actually be colliding with the sun or not? We actually think that most of the moons actually formed in a way that's almost like a mini model of our solar system, just through accretion around, and then essentially segments of the accreting dust around Jupiter formed in planetesimals that eventually became the moons. Now, I'm not sure about gas giants orbiting close to their suns, although we've seen they're very fast and they can be very close to the sun, so very hot, and we wouldn't expect them to have life as we know it. How are they maintained? I'm not sure what you mean by maintained.
It probably means the orbit remaining stable for that long duration for them to have formed gas giants.
Yeah. That's such a good question. It might be that that orbit is decaying, so it won't be maintained. It's just that we can't see it on the time scales that we're observing.
Yeah.
Very, centimeters per year or something.
Mm-hmm. I agree.
Right, you're the orbital mechanics guy. You can answer. Anyway, let's see. Can we use photometry method to detect in other planets? Photometry. Well, so by photometry, it can mean many things, but that is definitely one of the ways we do detect exoplanets, right? And is by looking for tiny changes in the amount of light that's getting through to our telescopes, and from that we can, and that the periodicity of that tiny blinking allows us to calculate the presence or predict the presence of planets, and that's actually a direct observation. So that's a good question. And actually, Biswaji, I don't know if you know about. There's a great app. It's called Exoplanet, and I have it on my phone, and it's so cool because there. I don't know if you can see this. It tells you every time a new exoplanet is discovered. And it just means I'm a little bit nerdy, but it's kind of fun to get an alert saying the database has been updated, and now we know that there are over 8,000 exoplanets that have been either detected or postulated. So that's cool.
So how often do you get these alerts then? Once a year or?
Every month or so. Yeah, I mean, it's just whenever someone uploads on the database, right?
Right.
So I recommend it for all you guys. It's free. Let's see. We didn't initially look for life on Venus, but since the current findings of phosphine, because of these current findings, would we rethink our search for life on other planets? Yeah, that's a good question. You know, I'd have to look into this more, but as I was thinking about today's lecture, I was reading that we have seen phosphine in the atmosphere of Jupiter, for example. So what does that mean? I think the detection of any molecule that's typically biologically or produced biologically on Earth is, to find that somewhere else is exciting. But I think there are a lot of things we don't know. And for me, anything that encourage exploration, I would support. I know there are other. In fact, a few of our colleagues have proposed a mission concept to the atmosphere of Venus, thinking that might be a less hostile environment. There could be microbes and other that could be floating in that dense atmosphere, and not have to contend with the hot temperature and acidic conditions on the surface. But so it might rethink it. We might lend support to looking for life in the clouds, right? Which would be, we've always thought about landers and rovers. So how can we make a vehicle that could look for life in the clouds? Kind of cool. Oh, surface materials. Okay, let's see. We learned from John's talk earlier that dust lanes are where stars are born. How probable are these dust lanes as habitable zones? Okay, that's a really interesting question. And in fact, we've seen that through telescopes, we can see that there are grains, right? Diffuse interstellar bands, and there are dust grains, and that if we just point our telescope in space, we can see evidence of silicate dust, and we also can see evidence of amino acids. So we think that we can form these building blocks in the interstellar dust. It's pretty exciting, and we know there are molecules of water and carbon, monoxide, dioxide, all these things. The question is, could they come together to go to that next step, which is life? And it seems that would be challenging, but I'm all for believing in the possibility. Kind of big answer, but anyway. Let's see. A question. I'm not sure. I'll be able to answer this one. It's a question about the Mars Perseverance mission. It's my understanding that the mission decided to land on Jezero because there's strong evidence to believe that it used to contain a body of water. Oops, sorry, that question. Given Perseverance's astrobiological main goals, why was the landing site not decided to be near the poles, close to, sorry, the question keeps, oh, close to the interface zone where you might see ice and liquid water? Okay, so why was Jezero picked as a target site? So the way we pick target sites on Mars right now is that the scientists think about where's the most exciting science place, and then the engineers rein in our enthusiasm. So right now, we try to land at a site that's near the mean elevation, or mean, what does it say, MOLA? Mean, anyway. But anyway, Mars has a dichotomy in elevation. The northern hemisphere is about 3 to 5 kilometers lower in elevation than the southern hemisphere, which is older and has
laser altimeter.
Okay,
right?
laser, but what's the O?
Orbiter, Mars orbiter laser.
Mars orbiter laser altimeter. So essentially what the elevation is on Mars. So we want to keep MOLA to, around 0 or down, like Gale crater was -5. So because that landing at lower elevation on Mars means we can take advantage of the aerobraking from the Martian atmosphere, which is thin, but it's densest at the surface, and that means we don't have to carry as much fuel going to Mars. Now there are other ways to get to higher elevations on Mars, and higher latitudes has a similar idea in terms of it takes more slowing down and more fuel to get to northern, or rather more extreme latitudes. So it's essentially a challenge for the entry, descent, and landing engineers. But besides from that, Jezero is pretty exciting because it does have all these sort of fluvial water features. And the thought is, if on Earth we tend to form these delta features or alluvial fans through rapid deposition. So one of the arguments there was that something that was deposited under alluvial fan, or a delta, so any sort of organic material, would have been deposited quickly and therefore had a higher likelihood of burial and survival and preservation than something that was just formed on the surface and then essentially vulnerable to any kind of radiation. So Jezero was, and with the case of the NASA sites, it's pretty exciting because they open up to the world. Anybody can have an opinion, and then they little by little they narrow it down to group meetings, and anybody can attend. It's open to the world. You can call in, or you can fly and attend in person. You can propose sites, and so they really narrow the target sites down to a few, and then headquarters, the chief scientist headquarters, picks the final landing site, and then the engineers have to okay it. Okay, that was a long answer. Sorry. Our field artists hired in the Braille mission. Oh, we would love to have field artists. Now, right now during the pandemic, it's a little challenging, but we are actively working there through next year. So, Christine, contact me and tell me about what kind of art you do. I'm sorry, I'm skipping some of these just because the screen's moving. What microbes are predominant in these low light mineral environments? Azul, that's good. That's a good question. Well, what microbes? Well, we see, one thing that's kind of interesting is we think we're seeing almost a 50-50 proportion of, what do you call it, lithotrophic, or rather lithotrophic or autotrophic microbes as heterotrophic. Oftentimes you'll see in a microbial community, you'll see, by autotrophic, I mean that's the organism that takes energy either in light or in rock or water. So it takes energy from outside and grows and reproduces. A heterotroph eats those guys. So oftentimes in a community structure, you'll see autotrophs, and then it's sort of like a reverse pyramid. So the heterotrophs will get more and more complicated and more numerous. And in this case, we see many more, a higher fraction of autotrophs. This is based on lipid geochemistry and also some of our metagenomic studies of the caves. And there are many more aspects to your question, but I think I don't have time to answer them right now. Are asteroids candidates in the search for life? Okay, so that's, so Lisa, that's a good question. And Ceres now has been upgraded to a dwarf planet, but it was considered an asteroid just because we think it has some kind of mushy or liquid interior. I think a lot of times asteroids wouldn't be good candidates just because they wouldn't have a source of that liquid water, whether on the subsurface or the surface, right? So they probably wouldn't be a high priority target. Could a collision between a proto-Earth and Ceres, maybe something else like the Moon, result in liquid transfer between the two bodies? Why not? Yes, I think so. Okay. Oh, how do the tidal forces affect the planet or moon's habitability? Okay, that's a good question, because I mean, they can definitely, because they can help with creating energy gradients, whether it's or any kind of gradient, like a gravity gradient, yeah, essentially a gradient. And we think we find most likelihood of life, or life on Earth at least, at along boundaries, right? Along boundaries, whether it's air, sea, ocean, rock, whatever, in terms of microbial life. So that's exciting to think about tidal forces. Oh, and Enceladus, yes. Okay. Do we have any idea as to the mechanisms that are creating the plumes on Europa? And why Enceladus are stronger? Okay, so we don't know exactly why we're seeing these plumes. We think, again, it's some kind of conduit of material rising with due to lower gravity, or rising up, so being more buoyant than the ice, and then breaking through. And why the Enceladus are stronger? It's not so much they're stronger that they're huge, right? Enceladus is so much smaller, so these plumes could, they can escape. The gravity is much smaller on Enceladus. So one reason could be that they can just extend further out because they don't have the same gravitational pull that Europa does. Or it could be that there's more heat driving that eruption, and then there's just actually more massive material. I don't think we know at this point. Okay, what causes the moons to have such a variation in surface features? Oh, that's a great question. That's like Europa has so many of these variations in surface features. That's the gazillion-dollar question we want to know. I mean, when we see like Europa that has all these really stripes, are these ice blocks? Is there ice tectonics on Europa? Does it mean the surface is active? The fact that we don't see craters, it's constantly moving, and so that's exciting. We think that when we see a lot of craters, it means there's not much activity on the surface, just because it's showing all the scars of getting bombarded in our solar system. So I just think we have a whole variety of different bodies to pick and choose from, and that's why we see the variety. Hey, I wanted to ask, are there any of the other instructors or lecturers who want to jump in and make any comments to these questions? Please feel free to join. I'm sort of blabbing here. I mean, especially Michael, do you want to answer, for example, or rather make a comment about actually maybe not the variety of life in the lava tubes, but just why we see different life forms in different environments?
Yeah, sure, happily. So I mean, you've covered most of this in the answers to the questions, but it's effectively where there's the minimum resources for them to be able to thrive. And when it comes to just single-celled organisms, there are the alternate pathways through which they can live and survive. So there's either phototrophy, where life is derived from light, or chemotrophy, where it's derived from chemical energy. And in a cave, it's a pretty bad site for phototrophic organisms. So obviously there's selection for chemotrophy. But what's very exciting with that is the extreme relevance of chemotrophy that's argued for example, Martian environments, not just the subsurface, but because there's a lot of research arguing that on the Martian surface, because of the interactions not just with ultraviolet radiation, but then the bactericidal effects of that with perchlorates, anything on the surface would just be immediately eviscerated. And so darker environments are the most likely for being considered candidates for habitable environments on Martian sites. But it's really the environment selecting. Like if you need a lot of sulfates in order to yield energy for growth and reproduction, and there's minimal sulfate in an environment, well, if there's lots of iron, something that uses iron instead will probably come to dominate, and you'll be pushed out or unable to colonize.
Do you think studying the microbial ecology in darkness, but in an air environment, is relevant to studying microbial ecology in darkness, but underwater or in water?
Oh, good question.
That's a very good question. I think studying microbial ecology in an array of different environments is important for defining interactions between species and community-dependent viability. So it's really cool what you were saying about the microbial communities you observe in the caves, where it's autotrophs, so they're fixing the carbon dioxide, they're getting the carbon, and then the heterotrophs are eating them, or eating the carbon they leak. We see pretty much exactly the same system in the Arctic springs that we work with, where it's carbon poor. So there's mostly autotrophs fixing the carbon dioxide, and then heterotrophs that can only be there by surviving on the carbon that's given out. So I think that there are some ecological principles that are perhaps universal between different environments. So what we see in hydrothermal vents holds for what we see in caves. And I think that it's from learning those ecological principles and trying to define more interactions between different functional groups of microbe, I think also gives us a lot of valuable information for developing hypotheses about habitability. Like if we test, okay, under Mars-like conditions, can this one type of microbe grow? No. Okay, but if another species was also present, would it then be able to grow? And that's a super important consideration for when we're considering viability. You know, it may not be this small subset of autotrophs. It might be a greater diversity if they're present in combination.
You just raised a couple of great points, including the fact that we can't do experiments in isolation and expect them to be representative of the environment. We need to look at a community. And even when we sample, right, we sample in a couple different ways. We sample by taking, physical samples and then doing the 16S or the 18S. So looking, and then we sampled also by just doing a total DNA distraction and then doing essentially a sequence analysis of all that muck, right? So, we're trying, excuse me, Michael, not all that muck, all that really valuable DNA. and then it becomes a data mining exercise, right, to try to figure out what we can find there. And we're still missing a lot, both in terms of what we can identify and what we know. And sort of, we're still just based, we can only extract information based on other things we know. So it's actually really exciting to think about what we don't know. And then I just get tired. But anyway, so maybe some of the people who are listening in will be the people who can tell us all the answers one day.
So to understand, it's more like you're not just looking for a special bug or the remains of a bug. You're really looking for ecosystems. You're looking at the environment and the different kinds of communities that would be living together. It's really interesting, and also what makes, I think, life hard for people working in astrobiology to understand it. And that's also why analog sites are important, but they also kind of make things difficult because there's all these other factors that kind of have to be reduced and removed from the equation.
Well, this is what keeps us busy. We just have to pick away at things and just not get discouraged. And if we go down a trail that doesn't seem to be very, very fruitful in terms of learning things or maybe getting resources to do that, then we have to pick a new trail, and there's always something to do. So that's actually very, very exciting. But yeah, my life, for example, in these caves, I really want to know who or what what groups of friends are secreting these, or helping to create these things that look like corals you'd see in the oceans that would be carbonate. Instead, they're 90% whatever cryptocrystalline or amorphic silica.
Jen, do
But
you
their
have
shape is very similar, and it's so exciting. You know, I'm like, why can't I look it up? Why can't I look up the answer? Instead, we're trying to pick away at it very slowly.
Jen, do you have more information on lava tubes on Mars? Do we have any potential sites that are of interest?
You know, I have to go dig them up, and I don't really want to have people wait while I do that. But the cool thing is a few years ago, a group at the U.S. Geological Survey used machine learning to go through all of the high-rise orbital data and pick out anything that looked like it could be a lava cave. And they found over 1,200, they call them candidate caves. So they found over 1,200 candidate caves, and they put them in a candidate cave catalog that you can get. And it's exciting because it wasn't all at super high elevations. There were a few hundred at lower elevation. And I certainly think it's exciting now to really think about the possibility of the mission. And now working with these folks at JPL who are really, the Boston Dynamics is the company that made that robot who can do backflips, right? And they make the dog robots. So JPL isn't creating the robots, but they're creating the software that allows these robots to behave on their own without a joystick. And so that's the exciting part. And this robot walked into Valentine Cave, walked up lava ledges, walked down the lava flows, and didn't fall over. And so we didn't know if that would happen. So that's very exciting. And now they're proposing to have like little packs of dogs for Mars, where if they have to go down a cliff, they'll be able to tether each other to a rope. And it's really wonderful to talk with them. They have all sorts of really interesting concepts. Afshin, you probably know some of these guys. They're so exciting to talk to.
Yeah, they have something that's like a crawler, a really small robot that can crawl up cave walls and basically do simple detection. Yeah.
They have eels that melt down in the ice for Enceladus. They have spiders. It's cool. So yeah. I think in our lifetime we will have robots doing a lot more on planets and moons. So I'm very excited about that.
Jen, did you have any videos? We would love to see them of the
You know, I can put them on the classroom page. But yeah, we do have some.
That'd be great. That'd be awesome. And I'm also interested to know if we are doing this, then there's probably going to be a lot of modifications to the rovers, because in the reduced gravity environment, the dynamics of it and all of those things. So probably, I'm not sure if they're already doing it, but are they actually looking at the mobility of the rover in reduced gravity environments, probably tethering them? And
yeah, I think we'll go to a lunar lava cave before we go to a Martian one. So you could use the moon as a practice ground, a practice location. Yep. And I don't know of work that's active in this area to see how they'll perform in low gravity, but I do know that the lead in the JPL group, person named Aliaga, is talking with Boston Dynamics and urging them to go in that direction. Yep. And he's taking them and showing them pictures of our recent trip and inviting them to come out and and experience the glory of their dogs walking in caves.
What about Heard Island, somewhere like that? There are lava tube caves there. What about something like that's quite extreme? Heard Island?
Where?
Antarctica.
Oh, which island?
Heard
Island. You know what, Emily? I don't know Heard Island lava caves. I know Australia has some in the Northeast.
Yeah. For sure.
I think any caves would be awesome. So this group has been working for a few years, and they've been competing in a Department of Defense competition, which is they have challenges every few years to help push the technology to the next level. And so they've been working in mines and underground tunnels, and now they're coming out of those man-made structures to work in the caves with Braille. And so they're bringing that technology to the lava caves, and it's exciting because it makes Braille, I think, a better project, but also it gives them a lot more challenges to have to confront this irregular terrain.
Yeah.
Okay, I'm just browsing through some more questions. Let's see.
Oh, sorry. Jennifer, do you believe that the human scientists will be included in the decadal survey at some point? Could you tell us a little bit about the planetary science and astrobiology decadal survey? This is from Flora Dutra. Flora, every 10 years, NASA, actually, there are decadal surveys happening all the time, but every 10 years, NASA commissions a decadal survey for planetary sciences. And this one is called, this year it's called, for the first time, Planetary Sciences and Astrobiology. And that's something where they, NASA pays the National Academy of Sciences, so an independent body, to solicit input from the community. It's usually from Americans, right? Because NASA research is supported by American tax or US tax dollars, but anyone can submit a paper, and there are typically 7 pages of their position paper, and you're invited to state what you think NASA should make a priority. So as you might imagine, I submitted one on caves, but some of my friends, submitted other ones on caves and other topics, salts, whatever, lots of different topics. They received, I think, over 800 of these. And then a committee has to read them all down and create a document that then NASA will use the document as a guideline when it goes to Congress to ask for money. So it's a very slow process, but it actually has value for that. And in terms of human sciences, for this decadal survey for planetary sciences, it's not so much for human missions. In fact, I did ask about that, but there are other surveys for human missions too, right? So for astronaut activities, and in this one, the more human-based things, we had a whole big contingent on diversity and inclusion and equity. So they were actually asking for papers to how we can increase our diversity and inclusion in the sciences, and a lot of papers went on that topic.
Jen, I had a question for you, and this is probably based on your experience, at NASA. So when NASA goes about prioritizing its missions, life detection missions, right? It obviously banks on available knowledge, and that's based on models, that's based on experiments and observations. And then on the other side, it also has to rank proposals based on the quality of the proposals. So for example, a mission that has been really well defined for, let's say, Enceladus, for example, as compared to a mission which is not completely as well put together for Mars or for Venus. So how do you make that kind of balance between where does NASA go? Is there a general sheet, like you had your own list of priority targets? Does NASA or any of the other space agencies do they maintain that kind of sheet, and how important it is to consider the quality of the proposal and also the logistics and engineering that is required for it?
Okay, so right up front, I have to say that I'm not privy to the decisions at the top level.
Yeah.
I'm a few levels down, but NASA has different classes of missions, right? And then they have an overall agenda. So they have something called discovery missions, which are about half a billion dollars. They have something called New Frontiers, which are usually around $1 billion, a little bit above. And they have something called a flagship mission, which is usually one that's part of the NASA headquarters. That's one where NASA decides as an agency, we want to put our money into this. So the Curiosity and the Perseverance rover or that kind of mission where it's multiple billions of dollars, and they make a commitment at headquarters, right? Whereas they have a little more latitude for some of these, like the mission to Triton. That's going to be, I think, a discovery mission. So sounds crazy. What can you do for $500 million? Well, you can do a flyby. You can do something in an orbiter. You can't land. It's too expensive. Engineers are expensive. But that's a good question. I don't know. I think I do know that again, you don't just send a proposal into NASA and hope it flies. There's so many little steps you have to take, and you are encouraged or discouraged along that path. So it takes years to get to that point where you are getting a mission to go.
And then again, the priorities.
They'll weed out the weak ones, or if you need help, they'll bring in help. And
the priorities also keep changing, right? Like every few years we see changes in which way we want to go. And this Venus
right.
announcement might also change things.
it might change things. And also I know that there have been times in the past and even now when, now that we have, our government has declared that going back to the moon with people is a priority. Well, human missions are 10 to 100 times more expensive than robot missions. So if we don't have the funds, then that's a priority, and that means the funds have to come from somewhere. So probably some of the funds from the science will come to support that.
Humans,
yeah. It's just constantly, it's one of, we have to look at it, we have to frame it so we look at it as one of the fun challenges of life.
So I just wanted to chime in really quick that before the paper about the Venus paper just came out, NASA actually announced a flagship mission to Venus earlier this year, much before this paper was even available. So they are already holding, I know JPL held this competition that was open to public, where they are accepting concepts from student teams on how to design a lander for Venus. Obviously, for flagship missions, they'll always start with something going in the atmosphere first, and then the next step would be towards landing on Venus. But NASA did commit to Venus missions, which will potentially be like a life detection kind of mission.
I remember reading that. I've seen it. I don't remember the name of the mission. Do you?
I don't think they have named it yet, but this was earlier this year, before the COVID shutdown and everything started, probably in January or February when they announced.
We have a colleague who we met in India actually, but he's a professor at University of Wisconsin-Madison, and he has spent the last 10 or maybe who knows how many years of his life traveling around the world advocating for Venus.
25, 30 years at least, yeah.
25, anyway, and he's completely obsessed. And I have to say that, I mean, when I'm listening to him, I believe everything he's saying, and then I come out of my trance. He's just so good, and so I'm so pleased with that. I remember reading that this year, and being very pleased for him.
He led the paper that came out in Astrobiology last year, along with Dr. Rakesh Moghul and Arif Ansari from India and Parag Vaishnapayan from NASA JPL on the UV absorption, spectroscopy studies from Venus clouds as well. So that was one of the most well-read papers of astrobiology. They actually highlighted that paper recently.
Really? Well, okay, that's great. In fact, we should share that with the classroom then. That'd be good.
Yes, that'd be great.
Yeah, and that was for a mission that would essentially be a floating mission with a payload to look at study.
And right now with India, and the other variable which has hit a lot of these missions is COVID, of course. So launch schedules have been delayed because of this. And India had in fact announced a Venus orbiter mission called Shukrayan, which was supposed to take off in 2023. It was a Venus orbiter mission. But now, in fact, in our own inaugural class, Dr. Srikumar, he announced that it will probably be delayed to 2025. And that's 5 years from now. And I'm just thinking with this Venus announcement, they might even, try to strengthen the capability of phosphine detection or try to have a stronger astrobiology instrument on that orbiter. Who knows? It might be something that might be announced.
So that's exciting. And I did see that it had, I actually was very happy to see that even though it had been delayed, it was not taken off the list. Because
absolutely. In fact, ISRO was planning to go to Venus even before Mars.
Yeah.
The second mission to Mars. So
yeah, that's
exciting for all the Venus champions in the astrobiology.
Well, so you're going to have a challenge to fit in all the exciting missions next week, Sid.
My slides are not even ready because I'm afraid what announcement is going to happen tomorrow or the day after. So I'm waiting until Wednesday to complete my slides.
The historical ones, I find going back at one point, actually some years ago, when I got my first iPad, I thought I was going to draw all the orbiters and landers on my iPad because I was so excited. And so I thought that would be a good art project. And in the process, I was reading about all the missions from the 60s and 70s and, Apollo time and just afterwards. And it was so romantic.
Yes.
And it was really cool. And then I got, anyway, I didn't finish because I got so stuck in the older literature. And, just like the Voyager 1 and Voyager 2 that now are out, I think, Voyager 2 is actually out at the Oort cloud now. I mean, it's just so cool.
Yeah.
And these are things you know, we have more computing power in our cell phones than this whole mission had. So it's exciting.
Absolutely. Yes. One thing we can try to do is collect really nice, full scale images of planets of all these different targets and make nice collage of that. Just like you had that slide with all the listed, so that'd be nice to have all of them together.
That'd be cool. And in fact, you know, a few cases, I apologize for this, but in a few cases, my images weren't, they either weren't referenced or they weren't in as high resolution as I'd like. And I think before I put that on the drive, I'll try to clean that up a little bit. But
that'd be great.
But, yeah.
Okay. You want to take maybe one last question before we end today's recording? And that's just to say that we'll be saving all the other questions. We've received over, let's see, 80 questions today. So we'll try to store all of them. We've answered about 18 already, actually 24 already. So.
Okay, well, you pick one. There are a lot.
Let's see. How do life detecting instruments work? I'll try to touch a bit about this next week. But Jen, if you had any comments, because you've worked with certain instruments.
Life detection instruments work. That, you know, that's a great question, and that's, I mean, that's one of the challenges. What would it take? I mean, this is a debate that's ongoing. What would it take to convince us that we had detected life? Because we wouldn't want to just make that claim. We'd want to be certain, or as certain as we could be, right? And I think the shortest thing to say is that we need multiple lines of evidence. So not just one instrument. We need some overlapping and some redundancy to have all of the lines of evidence support a finding of life, right? And other than that, if an alien walked in front of a video camera, I think we'd all be pretty convinced. But so I'm hoping for that one. But you know, little green men.
Yeah. So it's not a straightforward answer to, like many of these questions. You'd expect to be having straightforward answers, but they're not. And the reason for that is that there's so many different things going on in that environment that it's almost always difficult to confidently state that what you're looking at is life or not. And that's exactly what the challenge is. And it's important not to, you know, you won't be able to defeat this particular challenge right away, but to acknowledge it is, I think, the first step to be able to understand what exactly are these different challenges. And I think this talk that Jen has given us has given that first insight into the topic as to what are these different worlds, what are these different ecosystems. And next week, I'll hope to do at least a fraction of justice to what the speakers have done so far, towards trying to identify what are some of the technological capabilities that have been used in the past until now for detecting life, and what are some of the missions that are being prepared on Earth, as well as some of the ones that are already out there and which will be in fact improved. So some of the lunar missions that will be improved for Mars observation or Venus observations. So that's going to happen next week. I'd like to remind the participants that we are in fact receiving a lot of assessment forms, but we still need to receive a lot many more to be able to give you your certificates at the end of the course. So please do try to fulfill. I think the deadline for the first assessment on the analog sites is the 30th. That's in 3 days from now. So please do complete that. We're keeping a track of how many of them are coming through. And also there will be another Google form created where you can list 3 keywords that will be contributed to the glossary, as well as a feedback form for Jen's class. And all of that feedback is really, really important to us to help us improve our teaching, as well as, all our education tools that we're developing. So,
and I just want to say that some of these details might seem overwhelming, but when you're just sort of jumping into this very interdisciplinary field of astrobiology, you're in a really sort of exciting place, because you can ask anything and you don't worry about losing face. Or actually, the astrobiology is great that way, because I make no claims to know about every subject, and yet it's an environment that welcomes questions about things we don't know, and it's through that interdisciplinary dialogue is, I think, where you once again a gradient or a boundary where you find sort of the most exciting and maybe the most productive ideas. So in terms of where to look for life in the solar system, that was a serious question of mine. Is where do you all think? Where would you look, and why? Maybe you have an idea that we haven't thought of, or that the people who are the decision makers for missions haven't thought of, and because because you don't know where the great ideas have come from.
Absolutely. In fact, when the course started, I posted this question on Google Classroom, and a lot of students participated in that. And I think it was shifting towards Mars as the candidate side to look for life, but that might change maybe after this lecture. We'll see. All right. Well, we're close to an hour and a half. In fact, over 5 minutes. So thanks a lot, Jen. I think that was fantastic. The way you were able to deliver and do justice to all the worlds, keeping aside of obviously your own personal biases, but you also pointed those out to show why exactly you have these preferences, which is also very important as a researcher to do. So thanks a lot for that. Thank you, Michael, Annalie, Afshin, for joining us and also helping us out with the questions and your comments. And to the teaching assistants, Anurup and Tanvi and the others, Kat, who are not on the panel but are also sharing all this information and managing and doing such a great task with Google Classrooms. So we will again meet next Sunday and look forward to interacting with all of you next week. So thank you very much. Take care. Have a nice week ahead. So yeah, we'll just wait for recording to stop.